So what are acids and bases? Solutions are said to be acidic if they contain more acid than base, and they're said to be basic or alkaline if they contain more base than acid. If you remember back to our groups on the periodic table, we have the alkaline metals and the alkali earth metals. There is a reason for that, because when those are added to water, they form bases, so the words kind of going hand in hand. And then neutral solutions contain equal amounts of acids and bases. So the first thing we're going to take a look at is the very first definition of an acid and a base, and that was by a scientist named Arrhenius. He defined acids as they give off H+ ions. Now, just as a vocabulary thing, sometimes we refer to H+ ions as hydronium ions, which is H3O+, or as a proton. It's called a proton because if you think about the H+ ion, it's going to have 1 proton, 0 electrons, and hydrogen generally has 0 neutrons. So proton is kind of a shorthand of saying kind of the same thing as an H+ ion when you add things to water. So there's a few examples here: nitric acid, hydrochloric acid, and sulfuric acid. One of the things you'll note is acids always start with the letter H. So nitric acid, sulfuric acid, hydrochloric acid all have an H in front. That's how the easiest way for us to signify an acid according to the Arrhenius definition. Now, there's a 2 here. If you remember back to nomenclature, sulfate, the SO4 ion, has a -2 charge, so we need 2 hydrogens to balance that charge out, while both nitrate and chloride have a -1 charge. Arrhenius bases, on the other hand, give off hydroxide ions, which hydroxide ions are going to be the OH- when you put them into water. So bases are easy to identify because they both have they're going to have hydroxide ions according to the Arrhenius definition. So just like before with nomenclature, depending on the charge of your cation, it's going to determine how many hydroxides you have. So calcium has a +2 charge, so there's going to be 2 hydroxides. Sodium has a +1 charge, so that's why there's 1 hydroxide there. Okay, so Arrhenius was the first person to really take a look at acids and bases. However, he was missing out on some of the bases primarily. Bronsted and Lowery were 2 scientists that came up with a more inclusive definition for acids and bases. So what they said was that acids give off hydrogen ions while bases absorb. So the big difference here is when you are looking at the bases. The reason they came up with this was because of ammonia. Ammonia is NH3. And according to Arrhenius' definition, it is not going to be considered a base. So they added this kind of definition to help, because when you put it into water, it's going to become ammonium hydroxide, where you form a hydroxide. However, that definition isn't real inclusive. So the other thing that Bronsted and Lowery added is something called a conjugate acid-base pair. So a conjugate base of an acid is whatever the acid becomes after it loses the H+ ion, while the conjugate acid is whatever the base formed. So we're going to look, conjugates always appear on the product side of the chemical reaction. We're going to take a look at a reaction and start labeling it to better understand this concept. So what we have here is we have nitric acid when it's added to water. So nitric acid, what we're going to do is we're going to track the substances as they break down. So the nitric acid becomes the nitrate ion, and water becomes the hydronium. So looking at nitric acid to nitrate, it is losing a hydrogen. So that indicates that this is an acid. Now you might have already known, because it has that H in front, that it's an acid, which is something you can use to help you as well, but sometimes it won't be quite that obvious for these types of Bronsted-Lowery acid and bases. Water in this case is gaining a hydrogen, so water is going to be acting as a base. You might be thinking, well, water's neutral, how can it act as a base? We're going to get to that in just a moment, so hang tight if that's what you were thinking. So the acid always forms a conjugate base, and the base always forms a conjugate acid. So what you would look at is when you're going in reverse. So going from hydronium to water, you're losing a hydrogen, so that's acting as an acid. Also, hydronium is an acid. And then the nitrate is gaining a hydrogen to go from nitrate ion to nitric acid. So one of the things that I like to do here is I like to look at the reaction in reverse. So we have those reversible arrows. So we can write the reverse reaction. Oops, HNO3 plus H2O. So we can go through and identify these again. So hydronium with water. Oops, I forgot that plus. That's going to be my acid. Nitrate to nitric acid that's going to be my base because it's gaining a hydrogen. Water is then going to be my conjugate base, and nitric acid is going to be my conjugate acid. So things to point out here. If you have an acid like nitric acid, it's generally going to be the acid, no matter where it is in the reaction, and you can use that to kind of help you. Other things to point out here, you're going to always have the reactants are always going to be your acid and your base, and your products are always going to be your conjugates. So it just depends on how the reaction is written. So if you write the reverse reaction, what happens is your conjugate base becomes your base, and your conjugate acid becomes your acid. So you just use that word conjugate to help you identify the products. So we're going to be doing the same thing here. So we have this hydrogen sulfate becoming sulfuric acid. So that's actually gaining a hydrogen, so that's going to be acting as my base. And water is becoming hydroxide, so that's losing a hydrogen, so that's going to be my acid. So the H2SO4 is my conjugate acid, while the hydroxide is my conjugate base. So water can act as both an acid and a base here, and it uses this term amphoteric to describe that. Amphoteric meaning many. There are several amphoteric substances out there. Water is one of them. It helps you to determine it can act as either. So it's something you have to be careful of when you're looking at these Bronsted-Lowery acid-base problems, because you have to make sure you're identifying it properly. So in summary, we have this nice little summary table to help us describe this. So arrhenius acids are going to give off H+ ions, while Bronsted-Lowery bases are going to be giving off hydroxides. Bronsted-Lowery acids give off H+ ions, while Bronsted-Lowery bases absorb H+ ions. So the acid difference isn't really, it's not different. The thing that's different is bases, so you'll want to be careful when you're identifying Bronsted-Lowery bases that you're identifying things properly. So Arrhenius's definition, there's a few things that do not count as bases if you're looking at it strictly through the Arrhenius definition, but do count as Bronsted-Lowery. As we were looking, ammonia is one of those key examples. So what I'd like you to do is I'd like you to try these two examples on your own. If you look closely, you'll see they're very similar, so try those. So hopefully you try this, so you end up with ammonia as the base and water acting as the acid in the reaction on the left. The ammonium ion, NH4+, is the conjugate acid, while hydroxide is the conjugate base. And then the second one is just the reverse reaction. So what you're going to end up with is your conjugate acid becomes your acid, your conjugate base becomes your base, so on and so forth. So one of the things that we want to take a look at are some of the common properties of acids, bases, and neutral substances. So I've underlined the key ones here. Acids generally are sour in flavor, while bases are bitter. Now this is not so that we can test things in the lab that are to taste acids and bases. The reason we're doing this is if you're thinking of food items, common food items that are sour or bitter, you can kind of figure out from there. So lemons are very sour, or vinegar, because they are acidic. If you were to look at the texture of it, it would be sticky, while bases end up being slippery. Soap would be an example of a base. When you wash your hands are generally slippery. So this is just something to keep in mind. One of the things that we need to spend a little bit of time on is talking about the difference between concentration and strength. So concentration is a measure of the number of moles in a solution. Usually we express that in terms of molarity. That was what we talked about in our last unit. Strength refers to the extent to which an acid or base dissociates. So we have strong and weak solutions here in terms of strength. So strong mean they have 100% dissociation. Weak is everything else. So it can be anywhere from 99% down to 1%. Depending on the acid strength determines exactly where that falls. So when we refer to dissociation, it's just like when we have salts. So if we look at nitric acid, for example, nitric acid is going to dissociate into H plus and NO3 minus. So it's breaking up into the hydrogen and its ion. Bases, it's the same idea. If we look at sodium hydroxide, there are also strong and weak bases. It's going to break up into its ions. So not everything is going to break up 100%. As we discussed with equilibrium, not every reaction is 100%. This little graph on the bottom kind of helps to show it. So dissociation of a strong acid, this also would be the same idea for a strong base. After it's dissolved in a solution, you have 100% hydrogen, and then whatever the anion is, that's what the A is representing. But for a weak acid or base, after it dissociates, you still have a significant amount of your acid together that hasn't dissociated. So it just depends on what type of solution it is and some other nature of the acids or bases to kind of what's happening with it. So here's kind of some helpful hints for determining strength of acids and bases. So strong acids, there are only 7. The 7 are listed here. So the easiest way to identify if something is a strong acid is to check to see if it is one of those 7. If it's not, or 6 rather, if it's not one of those 6, you're going to assume it's a weak acid. There's a lot of organic acids, so like ethanoic acid, which is acetic acid, which is vinegar, is a great example of that. Bases, it's similar. Bases have the hydroxide associated with it. So strong bases generally have the hydroxide. Weak bases don't, so they have other things in there that identify them as a weak base. So I have a few particulate diagrams here kind of showing strong and weak solutions. So again, we're looking at acids, but this would also apply to bases. So how do you tell if something is strong or weak? So the little white circles are representing the water molecules, while the color circles are representing hydrogen ions and anions. So in this first one, letter A, you'll notice that there's a lot of acid particulates that are not dissociated. So that would indicate that this is a weak acid. If you look at letter B, it's the same thing. Most of the acid ions are together. So again, this is another weak acid. So the other idea here is that we're looking at the concentration. So which solution has a higher concentration? So we would say that letter A has a higher concentration, so we could say that's concentrated, while B would be more dilute. Dilute meaning not a lot of solute present. So if we compare C and D, you'll notice there are no paired acids and bases, acid. They're all ions. They're not paired nicely together. So both of these would be strong solutions or strong acids. And then looking at concentrations, again, this is relative. So choice D is more concentrated, while choice C is dilute. If you think of concentrated and dilute, think of like Kool-Aid or something that would be a bright color. So if you had concentrated Kool-Aid, it would be extremely dark, while if it was dilute, it would be lighter in color. So you could physically see the color. However, most solutions we make are clear, so that wouldn't necessarily be an indicator, but it's a great way to visualize it.